calculus with polar equations. We are interested in finding the slope of a polar curve. So to do that, we're going to need to define the derivative of a polar curve. So to find the slope of a polar equation, r equals f of theta. We want to recall from trigonometry that x is equal to r cosine theta. Well, if r is f of theta, then x is f of theta times cosine theta, and y is equal to r sine theta. But again, if r is f of theta, then y is f of theta sine theta with parameter theta. So here we are basically working with a set of parametric equations. So from parametric differentiation, how do we find dy dx? Well, we're going to do dy d theta, the parameter is theta, over dx d theta. So here I'm writing that as d theta of y and d theta of x. It's just that it gets a little bit more complicated because y and x are products. So using the product rule to find d theta of y, we're really doing d theta of f of theta times sine theta, that r sine theta. And so we're going to do the product rule. We take the derivative of the first function and we leave the second function alone, sine theta, plus we'll leave the first function alone, f of theta, then the derivative of sine is cosine. And to take the derivative with respect to theta of x, we recognize that x is r cosine theta, or f of theta times cosine theta, and we apply the product rule there as well. The derivative of f of theta is f prime of theta, and we leave cosine theta the same. And then we leave f of theta the same, and the derivative of cosine is negative sine. So that's why this is minus, and then f of theta sine theta. So we could think about it as a formula to find dy dx. It's this f prime of theta sine theta plus f of theta cosine theta over f prime of theta cosine theta minus f of theta sine theta. But I would definitely not recommend memorizing this. What it really comes down to is just understanding that x is r cosine theta and y is r sine theta, and then actually just applying the product rule each time.
All right, so let's do an example. Let's find the slope of the tangent line to the curve r equals 1 minus 2 cosine theta when theta is equal to pi over 4. So we'll start by saying we want to find dy dx. All right, well, that's dy d theta over dx d theta. And so that's d theta of y, and then d theta of x. But y is r sine theta. So the value of r is this equation right here. So we're taking the derivative of r, which is 1 minus 2 cosine theta, and then times sine theta. So this is r sine theta, right? And then the denominator is d theta of r, which is that 1 minus 2 cosine theta again, cosine theta. So there's my r cosine theta. So it's going to result in a product rule, right? So I have this product rule going on here. I have to do two product rules. I'm going to put a big fraction bar over here. So we have the first function, 1 minus 2 cosine theta times the derivative of the second, cosine theta, plus the second function, sine theta, times the derivative of the first. The derivative is of 1 is 0, of negative 2 cosine theta is going to be positive 2 sine theta. In the denominator, another product rule. 1 minus 2 cosine theta. So the first function, the derivative of the second is negative sine theta, plus the second function, cosine theta, and the derivative of the first again is 2 sine theta. Okay. So now, I wouldn't say it's really worth it to simplify because we want to find dy dx when theta is equal to pi over 4. So in other words, now we want dy dx at this theta equals pi over 4 value. So instead of, you know, maybe doing a lot of simplifying here, we'll just start to plug in pi over 4 into each theta. So here's what we have. Let's start with that numerator there. So let's see, we have plugging theta into each of these. We're going to have 1 minus 2 cosine of pi over 4 times cosine of pi over 4 plus, here we might want to simplify because we're just going to get 2 sine squared theta. So we'll get 2 sine of pi over 4 squared. On the bottom, I have 1 minus 2 cosine of pi over 4 times negative sine of pi over 4, and then plus 2 times sine of pi over 4 cosine of pi over 4. And now we'll evaluate these, right? And then simplify and see what we get. I've made some space here. So thankfully, each one of these is rad 2 over 2. Both cosine of pi over 4 and sine of pi over 4 is the square root of 2 over 2. So what do we have? 1 minus 2 times rad 2 over 2 times rad 2 over 2 plus 2 times rad 2 over 2 squared all over 1 minus 2 times rad 2 over 2 times negative rad 2 over 2 plus 2 times rad 2 over 2 times rad 2 over 2. Woo! All right, let's see what happens. So these 2's here, they cancel. And let's see, rad 2 over 2 squared, that's 2 over 4, which is 1/2. So this becomes 1/2. And the same thing happens here. This is 1/2. So 2 times 1/2 is just 1. So each of these is going to become a 1. And then let's distribute here and here as well. So we have rad 2 over 2 minus, all right, we're multiplying rad 2 over 1 times rad 2 over 2. That's 2 over 2. So that's just 1. So negative 1. Then we said this was plus 1. We get negative rad 2 over 2. The negative and the negative become a positive. So that's plus 1 plus 1. Okay, well, negative 1 plus 1 cancels. And so what are we at here? We have rad 2 over 2 over negative rad 2 over 2 plus 2. So let's clear fractions. We'll multiply the top and bottom by 2. So we get rad 2 over negative rad 2 plus 4. All right, that is our slope at the angle pi over 4. And now, as a follow-up question to the previous one, we want to find an equation of the tangent line to the curve r equals 1 minus 2 cosine theta when theta equals pi over 4. So here is the polar curve graphed, and I've actually also constructed the tangent line as well at the angle pi over 4. So pi over 4 is right here, and it turns out that that must have been a negative directed distance because the point of tangency is over here, opposite to pi over 4. So that's the point of tangency, and we found the slope of that tangent line already. So we found already in the previous part dy dx at theta equals pi over 4 was equal to that 2 over, I'll write it as 4 minus radical 2. So this is my slope, and what I also need is a point. So I need x and y. But x, remember, is equal to r cosine theta. And r is 1 minus 2 cosine theta times cosine theta. So what we need is we need to plug pi over 4 in to get out the value of x, and then we'll need to do the same thing for y. So we have 1 minus 2 cosine of pi over 4 times cosine of pi over 4. So 1 minus 2 times rad 2 over 2 times rad 2 over 2. So here if I go ahead and distribute in, I'm going to end up with radical 2 over 2 and then minus 1. So that's the x coordinate, and then we'll do the same thing with y. Y is r times sine theta, but r was 1 minus 2 cosine theta times sine theta. So we get 1 minus 2 cosine of pi over 4 sine of pi over 4. And we're actually going to get the exact same answer because of the fact that cosine and sine of pi over 4 are both rad 2 over 2. So here, when we distribute, again, it's the exact same value. We get radical 2 over 2 minus 1. So my point, my xy, is rad 2 over 2 minus 1, rad 2 over 2 minus 1. So we have our m, we have our x1, y1, and we'll plug it into point slope form of a line to finish out this problem. So we have y minus y1, rad 2 over 2 minus 1, equals slope 2 over 4 minus radical 2 times the quantity x minus x1. And we'll need to keep that x1, y1 in parentheses because the negative for each would distribute. And so we'll leave our answer like this. This is an equation of this tangent line when theta is equal to pi over 4.
In this example, I want to find all points r comma theta where the tangent line to r equals 3 cosine theta is A horizontal and B vertical on the interval from 0 to pi. So here, to find places where the tangent line is horizontal, I need to set the derivative equal to 0, and then vertical tangent lines happen where the derivative is undefined. So basically, I need the derivative. dy dx is equal to d theta of r sine theta, and then d theta of r cosine theta. So y is r sine theta, x is r cosine theta. Well, r is 3 cosine theta, so we're looking at finding d theta of 3 cosine theta sine theta over d theta of 3 cosine theta, that's r, times another copy of cosine theta, that's 3 cosine squared theta. All right, so up here in the numerator, I'm going to apply the product rule. So I'm going to leave the first function alone, 3 cosine theta. The derivative of sine is cosine. And then I'm going to have plus, I'll leave the second function alone, sine theta, times the derivative of 3 cosine theta is negative 3 sine theta. And that is multiplied there. Over, in the denominator, I need to apply the chain rule. So I would bring this 2 to the front, multiply by 3. So we're going to have 6 cosine theta. We need to leave that inside the same, times the derivative of cosine, which is negative sine theta. Let's go ahead and clean this up a bit. In the numerator, these both have a 3 in common, so let's factor that out. So we have 3 times the quantity cosine squared theta minus sine squared theta over negative 6, I'll put sine theta cosine theta. So this is dy dx. Now, again, to find horizontal tangent lines, so for part A, I need to find where does dy dx equal 0. And that's basically where does the numerator equal 0. And so I'm going to solve where does cosine squared theta minus sine squared theta equal 0. I'm not going to worry about the 3, right? Because if that were on this side, I would just divide by 3. So we're just going to focus on this part. And I'm going to go ahead and add sine squared theta to the other side. So cosine squared theta, when does that equal sine squared theta? I would definitely say that you could go ahead and determine what angles to substitute in to sine and cosine to basically get the same output, except that the signs could be off, like positive or negative could be off. So I would say you could go ahead and solve at this point right here. We're looking for angles only from 0 to pi. So basically, I'm going to put the answers down here for a second. So we have theta is equal to pi over 4 and 3 pi over 4. So those are the angles between 0 and pi. If I substitute in um, to this equation, the left side would equal the right side. So they would be off by a negative, but since we're squaring both sides, it's fine. Now, if you couldn't just kind of look at this and determine these angles, we could also divide both sides by cosine squared theta. And so the left side would be 1, and the right side, sine divided by cosine, is tangent. So I would get tangent squared theta. And so basically this would turn into two separate equations. If I take the square root of both sides, I'll get plus or minus. So I'm solving like tangent theta is equal to 1 and tangent theta is equal to -1. And so this might be easier to see, right? Plug in pi over 4, you'd get out 1. If you plug in 3 pi over 4, you'd get out -1. Those are the angles between 0 and pi that make this true. So however you want to work that trig equation out, these are the two angles theta. But that doesn't solve the what the problem is asking me for. It's asking me for the points, right? R comma theta. So these are just the angles. I need to go ahead and substitute them in to R to get the entire coordinate point. So here, if I do R of pi over 4, that's 3 times cosine of pi over 4, which is 3 times rad 2 over 2. So one of my coordinate points is 3 rad 2 over 2, comma pi over 4. And then if we substitute in 3 pi over 4, we get 3 cosine of 3 pi over 4. That one's going to be negative rad 2 over 2. So -3 rad 2 over 2. And my coordinate point is -3 rad 2 over 2, and then 3 pi over 4. So these are the 2 points written in polar where the tangent line is horizontal. Now, if we wanted these points in rectangular, what we would have had to do is substitute pi over 4 into r sine theta, where of course r is 3 cosine theta sine theta. So we'd have to substitute pi over 4 in here. That would get us a y value. And then substitute pi over 4 in here. This is r cosine theta. So this would give us an x value. So it is a bit easier to find the points expressed in polar. Now, here was dy dx again, so we could go ahead and solve for part B, which was find all places where the tangent line was vertical, which means we need to find where is dy dx undefined. And so we're going to go ahead and basically set the denominator equal to 0. So when is -6 sine theta cosine theta equal to 0? Now this one is a little bit trickier. I'm going to have to use an identity because I have these two trig functions involved here. And I can't really do anything at this point. So what I want to do is recognize that I can use a double angle identity sort of in reverse. So I'm going to rewrite -6 as -3 times 2 sine theta cosine theta, so that you could see a little bit more clearly, hopefully, that 2 sine theta cosine theta is the same as sine of 2 theta. And then we'll just bring down the -3. So when does this equal 0? Or divide by -3, basically when does sine 2 theta equal 0? All right, so what angles do I plug into sine to get out 0? So those angles that I would plug into this position right here in the 2 theta position, what angles would I plug in to get 0? Well, 0. So if what was right here was equal to 0, I'd get out 0. And another one would be pi. So sine of pi would equal 0. So if 2 theta were to equal pi, that would give me an output of 0. And then also 2 pi, sine of 2 pi is equal to 0, and then 3 pi, 4 pi, and so on. But remember that our angles theta have to be between 0 and pi. So right now, if we solve for theta and divide everything by 2, so if we divide all of these by 2, we're going to get theta is 0, pi over 2, and pi. So now these are the angles, and we want to find the coordinate points r theta. So we substitute them back into r. R was 3 cosine theta as a reminder. So r of 0, cosine of 0 is 1. So I'm going to get out 3. So I'm going to have a 3, 0. And then r of pi over 2. So cosine of pi over 2 is 0. So 3 times 0 is 0. So we get the coordinate point 0 pi over 2. And then if I do go ahead and substitute in pi, I'm going to get cosine of pi is -1. So I'm going to get -3. So I'm going to get -3 pi. So these are points where the tangent line is vertical, so it has an undefined slope. So now let's just take a quick moment to go ahead and graph the polar graph of 3 cosine theta. So 3 cosine theta is going to graph a circle, and that circle is going to have a diameter of 3, and it's going to be kind of shifted over to the right along the x-axis. So here is r equals 3 cosine theta. And so what are all of the polar coordinates where the tangent line is vertical? Well, we could see 3, 0 means go to the angle 0 and go 3 units towards 0. So that's this coordinate point here. And yes, absolutely, there is a vertical tangent there. 0 pi over 2 means go to the angle pi over 2 and don't go anywhere. Well, that's this point here, and there's absolutely a vertical tangent there. So what's this third point? Well, if I go to pi, which is over here, and go 3 units away from pi, it's going to get me to the same point as 3, 0. So this is basically a duplicate because polar coordinates aren't unique. So I don't really count this one here. I would just go ahead and say these two coordinate points are ones where there is a vertical tangent line. And then we got two answers for where is the tangent line horizontal. And so we could see that makes sense. There are two places where there is a horizontal tangent line. And those were at an angle pi over 4. So hopefully we can kind of see from my rough sketch that pi over 4, we would go towards pi over 4, what was it, 3 rad 2 over 2. So this coordinate point is a distance of 3 rad 2 over 2 away. And then we had 3 pi over 4, which is actually over here in quadrant 2, but then we had a negative directed distance, so it sent us away, and it would send us to this point right here. So all of our work checks out based on our graph of r equals 3 cosine theta.